This is the first lecture in which we're going to discuss the methods we can use to solve differential equations, not graphically, but analytically. And the first type of equations that we're going to be interested in are going to be called separable equations. And let's define what we're talking about. So the definition. A first order equation is separable if the following condition is satisfied. If we can write it in the form. So if it is in the form, y prime is equal to f of x times g of y. That is, I want to be able to write the right-hand side of the equation not as a function of x and y, but as a product of two functions, f of x and g of y. So how would you solve an equation like that? Well, number one, we can try to look for solutions of the following algebraic equation, g of y equals 0. Then let's suppose that we have, let's say, y0 is such a solution, which means y0 is a number that makes g equal to 0. So that is g of y0 is equal to 0. Okay, so then consider a constant function. Constant function y equal to y0. Of course, we know if we have a function, if we have a constant, so we know that in this case, if I take a derivative of y, that's the derivative of a constant, which of course is 0. So now we can substitute this into the ODE. And what do we get? We have that y prime, just like I stated a second ago, is equal to 0. But on the other hand, this is the same thing, or actually, let me write it like this. And if I take f of x times g of this particular y, then this is f of x g of y0, right? Because we assume that y is identically equal to y0. And y0, of course, is 0. So the outcome is 0 regardless of what x is, right? So this is true for any x. And so that means that y prime is equal to f of x g of y, because both are equal to 0. And so y equal to y0, identical equal to y0, is a solution. So this type of solutions, just like it was true for autonomous equations in the previous lecture, we're going to call these equilibrium solutions. Equilibrium solutions. Okay, so this tells you that if I want to solve a separable ODE, I can search for constants that make the function g equal to 0. And if I found a constant like this, then y equal to such a constant is automatically an equilibrium solution of my ODE. Okay, so that's one possibility. Second possibility. So now let's suppose that y of x is such that y is such that g of y of x is not equal to 0 for any x. Okay, so that means that in particular the graph of y of x cannot intersect, does not intersect any of these equilibrium solutions that I discussed in the previous item. Okay, so if that is true, then what do we have? Then I'm going to write my ODE in the form y prime. Actually, y prime I can express by using the Leibniz notation as dy over dx equal to f of x times g of y. And because g is not 0, right, by our assumption, then I can divide both sides by g of y, and formally I can multiply both sides by dx. So I can rewrite this as dy over g of y. This is equal to f of x times dx. Okay, so then what I have done, I separated variables in my equations in such a way so that the left-hand side only depends on y, and the right-hand side only depends on x. Fine. So if I have this, then derivative, then the function on the right, then the function on the left, I can take their antiderivatives because functions themselves are equal. Their antiderivatives must be the same. So if I take an integral of dy over g of y, this must be the same as an integral of f of x dx. Okay, so, and then what have I got? Once I integrate it, so in this case I cannot obviously explicitly integrate because I don't know exactly what f of y, g of y and f of x are. But if those functions are given to me, then in many cases I will be able to integrate. And so what I got is a function of y that is equal to a function of x. And that, as we discussed previously, this is exactly an implicit solution of my ODE. So here is then the procedure for solving a separable equation. It basically will consist of two steps. Step number one, you find the constant solutions by setting g of y to 0, finding y's that make g equal to 0, and then every y that you find by itself is a constant solution of the ODE. And then, in addition, to find the non-constant solutions, we separate variables just like so, integrate, and we end up with a family of implicit solutions to the ODE. Now, let's talk a little bit more where this thing comes from. Or actually, let me do a few examples and then we will do this discussion. So let's say I want to solve an ODE. So, example. I want to solve the ODE. Y prime is equal to y sine x. Now, clearly, this is a first order separable ODE. Because the right-hand side is a product of functions of y and the function of x. So then two steps. Number one, I want to solve. So let's label this sine x then is f of x, y is g of y. So first I need to solve g of y equals 0. In this case, it's the same thing as solving y equals 0. And so y equal to 0 is the only, so y equal to 0. So y equal to 0 is already solved. So this is the only equilibrium solution of the ODE. So I have my equilibrium solution. And so now I separate variables. So if we separate variables, we rewrite y prime as dy over dx. So dy over dx is equal to y sine x. Then separating variables gives me dy over y equal to sine x dx. And then on the next step, then I integrate both sides of this equation. Integral of dy over y is equal to the integral of sine x dx. So here is the first example of where you'll need to, of why you need to review integration from calculus, because now the process of solving actually reduces to taking integrals, right? Separating variables is really a simple idea and procedure. So the difficult part here comes from evaluating integrals. But in this case, fortunately, the integrals are fairly simple. So integral of 1 over y is natural log of absolute value of y. In principle, I would have to write plus C, but let us not do that for a moment. So natural log of absolute value of y is equal to integral of sine x, that is going to be minus cosine of x. And so now let's argue why we don't need to add anything on the left-hand side. If I did, I would add some constant c1 here. When I'm integrating sine x, taking antiderivative of sine, that also will produce another constant plus c2, but then I can bring c1 on the other side, get rid of c1, becomes c2 minus c1. C2 is generic constant, C1 is generic constant, so their difference is also generic constant. I can simply call C. So in this case, I only need one constant when integrating both sides, because the two constants that I got, I can simply combine together. All right, so this is what we got. So that means that this thing that I just found is my one parameter family of solutions to the ODE. And that's exactly what I would expect for the equation of the first order, right? All right, so I want to use this to solve a couple of initial value problems. Let's use this equation. Y prime is equal to y sine x. And let's say we know y of pi over 2 is equal to 1, for instance. Okay, so we're going to use the solution we already found. Because solution to the ODE we found, we just need to figure out what the value of C is going to be. So we need to take natural log of absolute value of y, so natural log of 1. It should be the same thing, right? So I'm using this one parameter family. And if I want a solution to pass through this point, I have to use y equal to 1 when x is pi over 2. So natural log of absolute value of 1 should be the same thing as minus cosine of pi over 2 plus c. Okay, and then what is natural log of 1? That is 0. What's cosine of pi over 2? That is also 0. So it follows then that c is 0. And therefore, solution of the initial value problem of my initial value problem is going to be natural log of absolute value of y is equal to minus cosine of x, right? Because c is equal to 0. Okay, so let's see, I want to then, so I found, this is an implicit solution. Let's see. That is the implicit solution. And let's say, right, because I did not solve for y, let's try to find the explicit solution. How can I do that? So if natural log of something is equal to minus cosine of x, then we can exponentiate both sides. And we have e to the ln of y is equal to e to the minus cosine of x. Then exponential and log are inverse functions of one another. So this will give me absolute value of y equal to e to the minus cosine of x. And I'm still not done because I have not found y, right? I found absolute value of y. Well, what does this mean? That absolute value of y is equal to something. It means that y can be equal to that something, can also be equal to minus that something, because when I take absolute value, sign will disappear. So it follows that y can be equal to e to the minus cosine of x, and it also can be equal to minus e to the minus cosine of x, which is not good because it means that my function in principle can have two different values. Well, here is where again the initial condition will come to the rescue. So let's see which check the initial condition. Let's see what we get there. If I compute y of pi over 2, what is that? That's either e to the minus cosine pi over 2 or minus e to the minus cosine pi over 2, which is cosine of pi over 2 is 0, e to the 0 is 1, so 1 or minus 1. But what's the initial condition? The initial condition is that y of pi over 2 is 1. So y of pi over 2 cannot be minus 1. So this is not good, right? Because our curve passes through the point pi over 2, 1. So that means that we need to discard the second solution. And once we have done that, so therefore, solution of the IDP is going to be y equal to e to the minus cosine of x. Right, so we solved the initial value problem completely. Now, let's say I want to solve another IVP. So another initial value problem. Same equation, y prime is equal to y sine x. But now instead of y of pi over 2 equal to, what was it, 1, I'm going to assume that y of, let's say, pi is equal to minus e. Okay? So what do? We repeat the same calculations, right? So we know that we have this one parameter family of solutions, which we found over here. So now I need to use that one parameter family to find the value of C. So substituting x equal to pi equal to y equal to minus C into this circled equation, I'm going to get the natural log of absolute value of minus e, that should be equal to minus cosine of pi plus c. Let's double check. Y of pi, so ln of y, yeah. All right, so what does that mean? What is ln of minus e? Ln of minus e is equal to ln of e, right? So I can get rid of absolute value. Ln of e is minus cosine of pi. Cosine of pi is minus 1, so minus 1 plus c. And so that means ln of e is 1. Minus minus 1 is 1 plus c. So, c is equal to 0. So then what do we have? So the same implicit solution as before applies, right? And that implicit solution was that absolute value of y is equal to minus cosine of x, right? Because if I go back here, we just found that c again is equal to 0. So ln of absolute value of y is equal to minus cosine of x. So applies. Absolute value of y is equal to minus cosine of x, with c being equal to 0. Well, again, if I want to find the explicit solution, in this case it's missing a len. If I want to find the same explicit solution, I can follow the same route. So exponentiate both sides. So that means that absolute value of y is e to the minus cosine of x. And again, if I get rid of absolute value, this means that y is equal to one of two things. Either it is e to the minus cosine of x, or it is minus e to the minus cosine of x, because both will produce the same absolute value e to the minus cosine of x. So once again, I'm going to check the initial condition. And what will I see? I will see that y of what we're using, pi. Y of pi, what is that? That's e to the power minus cosine of pi, or minus e to the minus cosine of pi. Cosine of pi again is minus 1, so it's either e to the minus 1 or minus e to the minus 1, which is either e to the minus 1, minus 1 is plus 1, so e to the 1 is e, or minus e. Again, I look at my initial conditions. I see that I want y of pi to be equal to minus e, so that means that only the second solution applies. So the second branch of solution satisfies. My initial value problem. And so therefore y of x should be equal to minus e to the minus cosine of x. So there is a single solution to this initial value problem. So you see that in this case, solving the problem explicitly always produces two possible solutions, and I select which solution I'm going to use by checking the initial condition again. Let's do the third IVP. And the third IVP is going to be y prime is equal to y sine x, if that's what our equation was, yes. And then I'm going to assume that y of 1 is 0. Okay, so I'm going to look back again at the one parameter family of solutions. So we know that absolute value of y, log of absolute value of y, is equal to minus cosine of x plus c. So then I'm going to substitute into this the initial condition. And when I do that, I am going to get log of what? Of absolute value of 0 is equal to minus cosine of 1 plus c. And I immediately see the problem, right? Because this quantity is undefined. Because I cannot take natural log of 0. Well, that seems to be a problem because then it seems that this equation, this initial value problem, does not have a solution. So does this mean that the initial value problem has no solutions? And to answer that question, we can appeal again to the theorem that we discussed a long time ago, a theorem which established if an initial value problem is going to have a solution or not. So in this case, right, so remember this result. If I consider an initial value problem, y prime equal to f of x y, y of x0 is equal to y0. And if I know that f and df dy are continuous, near x0, y0, then the initial value problem has a unique solution, right? So this is something that we certainly discussed before. So let's consider now our IVP, the latest IVP, the initial value problem. Y prime is equal to y sine x, y of 1 equal to 0. Well, if I look at my function on the right-hand side of this equation, so in this case, my f of xy is equal to y sine x, and df dy is just sine x. Well, y sine x certainly is a function which is continuous everywhere. Sine x is a function which is continuous everywhere. So both of those are continuous for all points x, y. Well, and then that means that the initial value problem, any initial value problem associated with equation, has a solution, right? By this result that we just recalled. So therefore, this IVP has a unique solution. But what we found here is that this unique solution cannot come from our one parameter family. So as we just saw, this solution cannot be found from the one parameter family of solutions. So what are we to do? We know that the solution exists. And so what are we supposed to do? Well, remember that actually our solution procedure consisted of two steps, right? One was to separate variables like we did. And the second step was we found equilibrium solutions. What is the equilibrium solution in this case? It's y equal to 0. And let's check. So if I take y identically equal to 0, then certainly the initial condition will be satisfied, because if the function is identically equal to 0, then it's in particular equal to 0 at x equal to 1. And because y equal to 0 is the equilibrium solution of my equation, that means that certainly the equation must be satisfied. So then, in this case, what can I do? I use the equilibrium solution. Y identically equal to 0. So that means that whenever your one parameter family does not result in a solution, you have to go back to equilibrium solutions, and hopefully one of them will work. Y equal to 0. Okay, let's do the last thing. So lastly, we're going to try to find a one parameter family of explicit solutions. So let's go back to the implicit family. So what we have is that absolute value of y is equal to minus cosine of x plus c. So c again is an arbitrary constant. Well, so again, I can try to solve this for y. I can exponentiate both sides. So e to absolute value of y, again, sorry, I keep missing the same thing, ln of absolute value of y is equal to cosine of x. I can exponentiate both sides and I'll have e to the ln of absolute value of y is the same thing as e to the minus cosine of x plus c. Then e to the power, let's write this separately, e to the power sum of two things is a product of e to the two separate powers. And again, e and ln cancel each other out, so I get the absolute value of y should be e to the c times e to the minus cosine of x. Now, what is e to the c? C is an arbitrary constant. So then e to the c itself is a constant, right? Because raising e to the power constant gives you a constant. But if you remember the graph of the exponential function, then exponential function has values that are always positive. So that means that e to the c must actually be a positive constant. So let's make a note of that. And let's call this d. So that means that absolute value of y is equal to d e to the minus cosine of x. Now, am I done solving this for y? No, not yet, because I still have absolute value present. And just like before, I can remove absolute value of y. If I do that, then I have to list two possibilities. Y can be either de minus cosine of x, or it can be minus de to the minus cosine of x. Okay, so then let's think about this in a little bit more detail. So what is d? So if c was an arbitrary constant, then d becomes an arbitrary positive constant. So d is an arbitrary positive number here. And if d is arbitrary positive number, what about minus d? Minus d is still an arbitrary positive. I mean, d is still arbitrary positive. You multiply it by minus sign, and this becomes an arbitrary negative number. Okay, so then y can be an arbitrary positive times the exponential, or arbitrary negative times the exponential. So what is the conclusion from this? Y is e times e to the minus cosine of x, where e can be arbitrarily an arbitrary positive or an arbitrary negative. So e is an arbitrary number, is an arbitrary constant. And note one particular thing in this case. So note that I got rid of ln, right? So there is no problem now that I had before when I had to take natural log of 0. So if e is equal to 0, capital E is equal to 0, then y is identically equal to 0. So that is my equilibrium solution is now a part of the one parameter family of explicit solutions. So you don't need to consider two different, don't need to consider equilibrium solutions as being separate from the one parameter family of solutions. But that is uh, only if you solve for explicit solutions. And by the way, this is also not universally true. In problems like this, it is true, but in general, it might be that even if you find the explicit solutions, the thing is that equilibrium solutions, some or all equilibrium solutions, are not going to be included in that. So a very good practice is to find both equilibrium solutions and one parameter family of solutions and use those. But anyhow, so in this case, you can say that all solutions of your ODE are encoded in this one parameter family of solutions. And in the next part, we're going to consider more examples of this method.